And the next talk will be given by Dr. Igor Dontsov. So Igor, please.
Okay. So hello everyone, and thanks for inviting me. So it's my pleasure to give a talk. So I hope I'll have enough time to finish. Otherwise, please stop me. So I have a good time for discussion. So so what I wanted to talk about is homogenization of high resolution rock properties. Okay. And the reason for this is, I mean, you can see basically in the background of my title slide, right? So in the background, you can see the picture of a core from unconventional reservoir. And again, right now, let's, hypothetically move to, West Texas, right? Where, all this, core is taken from. But the scale, the vertical scale is about 1 meter, right? Or 3 feet, if you like feet. And you can see that on the scale of about 1 meter, you have multiple layers. Even visually, rock is very, very different, right? And so the properties, of course, they are very, very different. And you all know that the fracture size, order of hundreds of meters, right? And so the question is, do we have to account for all this heterogeneity? Can we just average it? Do we have to do something special to upscale it, right? So these are the questions that I will be addressing, in this talk. To put it in a large scale perspective, again, speaking about applications in unconventionals, in shales in US and maybe Canada, China, and Argentina. So the trend is to drill multiple wells. Okay, so it's not just single well, single horizontal well. I mean, as you can see on the figure, it's a multiple wells. Okay, maybe here is a little bit exaggerated example, but I've seen projects with 10, 12, 15 wells, and they're drilled in different benches, different depths. Okay, and the way they complete it is typically the following. So they put multiple stages, say 30 stages per well, and each stage consists of maybe 5 to 10 perforation clusters. So essentially, if you need to model this, you have for each stage, you model, say, 5 fractures. Okay, and then you have 30 stages, right? So this 150 fractures per well. And then you have, say, 10 wells, right? So this is more than 1,000 fractures per pad, right? Per this development unit. Okay, so this is the massive scale of fracturing. Okay, and the question is, what do we do to model it? How can we model it, right? And on top of this, of course, this we have, I mean, as I said, we have this vertical, very high resolution of rock properties. Okay, so the rock properties changes on the order of centimeters, maybe tens of centimeters, while the fracture size is hundreds of meters. So how do we account for this? Okay, so this is actually this is a big problem. And on top of this, some wells could be producing for several years. They're called parent wells, and some wells are drilled next to the parent wells. So the question is, I mean, again, if you produce the well for say several years, you reduce the pore pressure, you reduce the stress around the well. So you need to account for this depleted stress. Okay, so this is the problems. Okay, the overall. But again, I'm going to focus only on one thing. But let me see, just to give you an idea how we address this scale development. Again, just going to give you a bird's eye view and then focus on one thing. So the first thing is how we upscale the rock properties. Something we did back in 2017, and this is what I'm going to focus on today. Second thing is how to upscale the number of fractures. As I said, you have thousands of fractures, and if you want to model the whole thing, okay, it's not just single planar fracture. You want to model the whole thing with real world trajectories, with real fractures and interaction between the fractures. You need to reduce the number of fractures, and so that's what we're able to do. And in a nutshell, you can replace multiple fractures within a stage with a fewer number of fractures. This is upscaling. Of course, you lose the accuracy to some extent, but again, you captured the main thing. For instance, here you have 2 configurations. One is original, you have multiple fractures. They're all weird because they interact due to stress shadow, and one equivalent, but which represents it from stress level. And here you have a picture right below, the stress field from this complex fracture system and a single fracture. And again, far field are the same. And then second, the next thing is how to model it quickly. And so we developed this ultra-fast hydraulic fracture model. Again, we've seen before meta models for planar fracture, right? But here we don't, and it was elliptical, right? But here we need to account for multiple fractures. We need to account for stress shadow between the fractures, okay? And so here, in contrast to use data science, we actually use reduced physical modeling, kind of like pseudo 3-dimensional modeling, but reduced even further to an elliptical fracture. So it's still physical model. You still enter all the rock properties, all the fluid properties, proppant properties, and so on. But it relies on some analytical solutions and approximations to give you fracture geometry, right? And so this is, again, we're able to achieve about, it's basically you simulate a stage in like half a second, roughly. Okay, that's kind of computational time. And again, we compared, from stress point of view, fully 3D model view on the top was one of the cases, and ultrafast, stress field, are the same. And fracture geometries we also compared. Okay, and finally, once you have the fractures, you want to compute production from all this system of fractures. And for this one, we created the fast reservoir model, again, some of which can run within a minute for this massive scale fracturing. Okay. So I'm not going to go into the details. If you give me 3 hours, I can talk about each of the topic. But right now, let's go back in 2017 when all it all started, and we'll try to understand how rock properties, can be upscaled, so that they can put in all this, bigger picture into the modeling of the spat scale and massive fracturing. Okay, so for typical model, okay, so we say our input properties are the fracture toughness versus depth Young's modulus, Poisson ratio, Leakoff, and minimum stress. Let's think about, for simplicity, about single planar fracture. And they can be high resolution. I mean, as I said, so if this is your core, now if you interpret the rock properties from petrophysics and stress, they're going to be high resolution, because, I mean, even if visually your rock changes, then the property change, stress change, and so on. Okay, the way how it changes, it depends on the model, but it's not that important for this talk. There were some previous studies on these topics. So previously, I did something in 2017. I considered a plane strain fraction a layered material, and essentially said, well, you can upscale stress in the middle of the fracture, but then near the tip, you still need to do high resolution modeling of stress. And while it's good for plane strain fracture, if you want to do planar, it's not good, because you still need to solve this near tip problem numerically, which is slow. There was a study from guys from Lawrence Livermore lab. You see it's on the right. So they simulated a planar hydraulic fracture in a periodically layered material. So the various stress, okay, from high stress, low stress, high stress, low stress, and so on, and observed this behavior. And the conclusion was that your stress oscillation, again, the average stress is constant, okay? But because you have stress variation, stress oscillations, your fracture seems to be more height contained. And they describe it with, by an additional vertical toughness being, this delta stress essentially times square root of layer size, okay? And they did a whole bunch of examples that basically fitted this equation, and this was their conclusion, okay? So let's address things one by one. So again, as I said, we have to consider elastic properties, stress, toughness, and so on. We need to homogenize all the properties or upscale all the properties. So the elastic averaging seems to be one of the easiest one. It actually was done back in 1962 by Backus in the context of wave propagation. So you consider this kind of cube of layered material, and you apply constant strains horizontally, and you look for average stresses, and then by counting for all the layers, you can get with some coefficients. I'm not going to go into the details, but the idea is, again, you're given the properties of each layers, you define some sort of weighted average of these properties, and this was done for TI material, transversely isotropic, right? And so we can compute the homogenized properties, okay? And again, homogeneous do not necessarily mean the average, okay? So if you take your, say, Young's modulus, you have high, low, it's not necessarily that your effective Young's modulus is going to be just simple average. So it's a little bit more than that, okay? Let's just a little bit go into elastic anisotropy, try to understand whether it's important or not. And so the elastic anisotropy has been considered before. So for instance, a paper by Laube and Ulm in 2014, they considered plane strain fracture in transversely isotropic material. And they concluded that, so if you kind of open it in a direction perpendicular to the two layers, and in this way, right? So think about, you have a 3D fracture, you have side view and top view here. You're gonna see a different apparent elastic moduli, right? So if you had isotropic material, then all these would be the same, right? But because it's anisotropic, they're slightly different. Okay. And here, just consider an example, right? So say what if you have again, periodic variation of Young's modulus, again, hard, soft, and the same Poisson ratio. How would this effective moduli change as a function of this stiffness ratio, right? You can see that if you have stiffness ratio, say 2 to 3, then your, so their ratio is about, so that they're different from the average, okay, is about 10-15%, okay. So again, so what I'm plotting here is the homogenized modulus, okay, based on this Backus averaging versus just simple average, okay. So if you ignore this mechanics homogenization, just say, you know what, I'm just gonna average it, okay. So your error is about 10%, so it's actually not that big of a deal, right? So, but we're able to quantify. Now let's go to the interesting part, okay. What happens with fracture toughness, right? So what if you have a layer with, thin layer with low fracture toughness followed by high fracture toughness, okay? And here I want to distinguish between the vertical and horizontal fracture propagation because they are very, very different conceptually, right? Think about here, the picture below, you have hydraulic fracture, okay? This is, think about your side view. And so the water or fracturing fluid is blue and it propagates horizontally in this layered material, right? So what you see is, fracture essentially contacts all the layers, right? So you see the average properties of all the layers. In contrast, if fracture propagates vertically across the layers, it feels just local properties or local toughness of this particular layer. And if you have one thin layer, which is very, very, very strong, you're not going to cross it, okay? Here on the left, fracture is going to go around it. Here it's going to be arrested, okay? And so the question is, how do you upscale this thin layer? How do you preserve it? Okay, and so here we introduce the concept of fracture energy. So it's fracture toughness over the apparent modulus. Okay, so this is like your surface area. So this is energy per unit area of the fracture, right? And we treat it differently in these two directions. So we say in the horizontal direction, okay, we're gonna take the average or the weighted average of the energy to homogenize toughness. In the vertical, we're gonna take the maximum, okay? So imagine if you want to homogenize again properties over the whole entire interval, it's the worst layer that's going to determine whether the fracture is gonna cross this element or not, okay? It's the worst layer, and we are looking for this worst one when we are homogenized, okay? So that's why we need to take maximum. Let's just give an example just to demonstrate that this is the case. So we consider the base case scenario, a nearly toughness dominated fracture propagation, single planar fracture. Here are the parameters, no Leakoff, this is viscosity, toughness, and so on. And here's the phase diagram for radial fracture, right? So we are near the toughness vertex. This is again toughness, this is viscosity dominated. And we want to be in toughness dominated because we change toughness, right? We want the solution to be sensitive to toughness. And then we alter the Young's modulus, okay? So instead of considering homogeneous material, we say we have all properties the same except the Young's modulus. So it changes from 15 to 25 GPa. So again, it's periodically varying. So we have layer of 15, layer of 25, layer of 15, layer of 25, and so on. And if you go through all these homogenization procedures I described below, again, so that you use the energy, and recall that Young's modulus enters the energy, and then you have the average in horizontal and maximum in the vertical, you come up after homogenization with the following homogeneous parameters, okay? And of course, the vertical toughness is going to be larger than horizontal because you have, maximum here in the vertical toughness. And then we run a simulator for planar fracture in a layered material where we change just the Young's modulus and all parameters are the same, and homogenized, where instead of this layered Young's modulus, we use homogenized properties, okay? And look at the aspect ratio, they are the same, right? Practically the same. And on the right, we plot fracture size, height and length for the averaged for the layered and homogeneous material. So the layered is your length is dashed black, and the layered and the length homogenized the red, right? So they pretty much match, and the solids are the height, right? So in the layered material, the fracture propagates and then gets arrested by one of the layers like a barrier, and then propagates again, and so on. In homogenized, it's kind of you average it out and you capture the overall behavior. But in contrast, you see, if you just do simple averaging, you can say, you know what, I just ignore all these high scale variations. You average everything, you're going to have a radial fracture, and its radius is going to be given by this gray line. So the homogenization does provide, does capture this behavior, right, on average, okay, and so that's very good. We then do the same example, but we vary horizontal toughness again. So you have a layer of 2 MPa square root of meter, and then 4, 2, and 4, 2, and 4. And then you homogenize, you get slightly higher horizontal toughness because you have, it's energy, right? So you have toughness squared average, okay? So it's going to be more than 3, so it's about 316 after this averaging or homogenization. And of course, you have this solution for the layered material, and then you have solution for the homogenized. You can see this kind of egg shape because you increase the horizontal toughness, which is 316, and the vertical is still 3. So you kind of have elongation in the vertical direction. And again, these things, match fairly well. And the vertical toughness, now let's jump from 2.5 and 3.5, again, periodic material. And as shown by these equations, we need to take the maximum, the worst layer, right? In this case, is going to be the maximum toughness, right? Because the modulus is homogeneous. And so after homogenization, so we have vertical toughness being 3.5. Okay, so it's max between 2.5 and 3.5. And again, we run simulations for layered and homogeneous material using planar model, and we see that the fracture size in terms of length and height, they match very well. Again, the homogenized is red, solid and dashed, and the layered is black. Okay, and so so the bottom line is that the layers can actually arrest the vertical height growth, thin layers, and if you do homogenization, we can capture this. Okay. Now the pinnacle, right? Stress, right? So we all know that the stress is the most important thing for fracture propagation, and stress variation is very, very critical in determining whether we're going to have height containment or not, or unbounded height growth. So how do we average stress? Okay, so the first thing is that the total force, think about, you have this in high resolution gray and homogenized black, total force acting on an element should be preserved, okay? What is force is stress integrated over area, right? And so that's why the stress should be just weighted average, okay? So we need to preserve total force acting, or in situ force acting on the fracture. But this about it or not? Because previously I showed that in previous study we found that near the tip you just cannot do it, okay? It doesn't apply. And so we need to introduce a correction. And so what we do near the tip is we notice that because we change the state of stress, okay, from high resolution to average, you can induce an additional stress intensity factor due to the difference between high resolution stress as shown here and the homogeneous stress sigma bar, okay? And we know the equation for the additional stress intensity factor due to this extra loading that we are neglecting, okay, near the tip. And if you take a minus sign for it, it becomes an additional vertical toughness, okay? So again, so the difference between the average stress, which we need to use in order to preserve the total force, and the actual stress causes an additional stress intensity factor, an additional apparent toughness, okay? And then what happens is that we compute this on high resolution, and then you use this maximum principle for fracture toughness, the maximum energy, as I described above, to homogeneous stress, okay? And so let's move on. So let me give you an example, okay? Let's consider example of periodically varying stress, okay? So you have stress varying from layer to layer. So you have the average stress, and plus you have this delta sigma, and this F is dimensionless function, right? A whole bunch of heavisides basically gives you this periodicity. Now you plug it in for this equation for computing an apparent additional toughness due to this stress difference between, again, high resolution and homogenized. You plug this delta sigma F, okay? And this correction is actually different for the fracture growing vertically and upwards and downwards, okay? And you can see actually, the function has different sign here, Z plus S, Z minus S. So your apparent corrections are going to be different for the two directions of growth. And so if you do the math, and once you integrate all these heavisides, you find out that this apparent toughness indeed scales with this magnitude of stress and square root of layer size, so H being layer size. And there is some factor, right? So some dimensionless function, and they are shown here. So again, so the F, so the blue line shows your stress, okay? So again, it's one cell, okay? It's one cell, so it's high stress and then low stress, it's normalized. And these red and black lines show the additional toughness, okay? These dimensionless functions GU and GD, so for the fracture growing upwards and downwards, okay, as a function of position along the cell. And the large N is number of cells which are used for integration, because here, again, we integrate to infinity, right? Again, it's near tip model, okay? We integrate we're assuming semi-infinite fracture, but of course we have to truncate it in actual computations. But we see that the results, can converge quite quickly. And here's how, they converge in error versus number of cells. But what is important, it's actually on next slide, is to try to understand how does this stress layering affects apparent toughness, okay? So if you have the semi-infinite fracture, okay, and then this blue line is your stress field, okay? So the apparent toughness for this fracture is the largest, it's right here at this point, when the fracture is about to cross the stress barrier, okay, about to cross and go into the low stress zone, okay? And it makes sense, right? Because here you have, most of compression near the fracture tip. On the other hand, for the fracture going downwards or in the opposite direction, this apparent toughness actually is symmetric, right? So it's flipped. And so the maximum actually occurs right here, right? So it's in a different spatial location. And so for this particular case of periodic stress layering, the actual maximum is the same, right? When you take the maximum, but the location of the maximum is different. But for general case of stress variation, the actual values of the apparent toughness for the fracture going upwards and downwards is going to be different. And if you do the math again, so we find out that for this particular case, this delta toughness is about 1.07 delta sigma times h to the 1/2. Again, delta sigma being this variation of your stress and h being the layer size, which again compares very well to what they observed numerically previously. But again, this is based on theory, right? On this analysis of the near tip region. So let's see what are the consequences, right? So again, we go back to our example. Now we introduce a layer stress with certain layer size is 20 meters and certain stress magnitude in 0.1 MPa. And if you do this, homogenization of mass machinery, you find that the effective toughness should be about 0.5 MPa squared of meter, the additional toughness, okay? And sure enough, when you run it in the layered formation, again, everything is the same, but you have periodic stress, okay, with this magnitude and this layer size. And homogenized, again, you match the aspect ratio. You don't match the exact details, of course, the width variation, but you match the details of height containment, which is very important. And then now you can say, yeah, let's see that this formula scales well. So we double the magnitude of stress. So you're going to have even more height containment. Again, it's a layered material, a solution for the layered materials here on the left. And so again, we double the effective toughness, and we do see that we match the height and length, and very, very well. Okay. Now, what if we change the layer size?
For 5 minutes left.
Thank you. Instead of 20 to 10, and again we see less height containment as predicted by the theory, and now we see it in numerics. So last thing, and then I'm going to stop, is Leakoff. Again, Leakoff is one of the input parameters, and we also need to homogenize it. And in a nutshell, there is nothing interesting about Leakoff. So basically, we run cases for layered Leakoff and homogenized Leakoff, and the fracture is pretty much radial. There is no extra height containment due to variation of Leakoff, right? I mean, there is some non-uniform growth, but again, it roughly follows the average profile. So we don't do anything with Leakoff. Right. So what are the implications? Right. The implications is that the vertical fracture toughness changes considerably. Okay. So if you account for these high resolution properties, okay, you change the height growth. Okay. So you effectively increase the vertical toughness by this magnitude of about 100% or order of 100%. Okay. So this is a big deal. Okay. And but the rest, they kind of follow the average, the stress, the Leakoff, elastic properties, but the toughness, the vertical. And here I'm not putting the scale. This is not 0, but you have this high resolution toughness. It's about, think about 1 MPa squared of meter. So this could be about 2 to 3. Okay, so it depends on your stress. So that's the big deal, and it's gonna change fracture containment. Okay, so let me skip this in the interest of time and just go to summary. So, so the idea of all this homogenization, right, is to represent high-resolution rock properties, okay, implicitly on a coarser mesh, okay, because we cannot run numerical simulators on 1 meter or half a meter resolution, like 0.1 meter resolution, okay. So we want to somehow implicitly represent this, okay. And if we do just simple average, the average of the properties, we can ignore certain effects associated with high resolution, so we're just going to smear them out. But if we do homogenization, okay, so we represent this high resolution property variation via an effective change of vertical fracture toughness, okay, and this change is typically an order of 100%. And this preserves the fracture height containment, okay, and which would be we would have if you use high resolution data, okay, and so that and the magnitude of toughness increase also depends on the resolution, right? So if you upscale, say 1 millimeter data to 1 centimeter, you're probably not going to see much of a change. If you upscale millimeter data to 1 meter, 10 meter data or resolution, you're going to see a bigger change, right? And another interesting fact, in a stop, is that the size dependent toughness, in which actually what we observe here, right? So as we say that the effective toughness depends on your homogenization length scale, but the size dependent toughness has been observed in laboratory experiment as well in observations of magma dikes, and they actually show that it scales roughly with square root over your fracture size, which actually aligns very well with our theoretical modeling. Okay, so thank you, and I'll be happy to answer all your questions.
Okay, thank you very much, Igor. So now we have a little bit of time for questions, please. Okay, so let me start probably. So when you say about this high resolution data, probably we need to take into account somehow that at least a part of this high resolution may be an error, like a noise in which we have because our measuring procedure is not perfect. So if we will take it too seriously, it may cause errors. So this is just a comment. So it would be interesting. How do you comment on my comment?
Yes, yeah, I think it's absolutely valid comment, right? And actually, I mean, we already had a little discussion that we have some uncertainties in the model. I mean, in the data, and this is actually one of the reasons why we decided to go with this ultra-fast hydraulic fracture model, because I mean, what's the point of running full-scale, very accurate model if your data is uncertain? Okay, but we still want to have a systematic way of representing this data, okay, in the model, so that ideally you would do multiple realizations, okay, or what if scenarios to see if this is real or not, or what is the effect is. For instance, you can use high resolution data, right? You can use core data, you can use log data and compare to see what is the implication on the final fracture result, okay? You can smoothen out the data, okay, and don't do homogenization, and just to see what's the effect, so it enhances understanding. Okay, but you're absolutely right. I mean, this could be noise, could be fitting. In this petrophysics, there's a lot of stuff going on, but given the model, okay, we now can predict, and then we can consider multiple models, multiple realizations to see what's the final effect of this modeling is. That's kind of the logic.
Okay, thank you very much for your answer. So maybe
I have one question.
Yes, Igor, please.
It's very short. Igor, have you tried to apply your procedure of harmonization to real data and real field parameters, or it was a model? I mean specifically harmonization of rock stresses.
Yes, absolutely. I mean, this was all developed in 2017, and we almost immediately started applying it for field data, for field projects. I mean, it's been applied to, I don't know,
because
a whole bunch of projects.
The question is simple, because in my field experience, the fracture toughness, you say that the harmonization of rock stresses leads to additional terms in fracture toughness.
Correct.
Yes. But my idea is that fracture toughness itself has little to no effect on the fracture geometry.
Oh, yeah. Okay.
In practical applications, because, well, of course, in laboratory you may achieve such situation when it's valid, but I haven't really met the situation when such fracture toughnesses would be important.
I agree. So here's a thing to consider, right? So it all depends whether you propagate fracture in the viscosity dominated regime or toughness
Yes,
dominated?
that's what's my question. So your regime was toughness dominated.
If you do cross-link gel, okay, if you use cross-link gel, right, then very likely it's going to be viscosity dominated regime, and the toughness is not going to be important. On the other hand, if you use slick water, you know, which is used, you know, here in Texas very often, is going to be shifted more towards toughness dominated regime, and so because viscosity is much lower. This is one thing. And the second thing, even in P3D model, okay, you have the horizontal growth, okay, is controlled by viscosity, okay, but the vertical growth is very often controlled by stresses and toughness, right? So this is a main assumption of P3D model, that, you know, the fracture propagates in the toughness regime vertically, and once you propagate in the toughness regime vertically, then toughness is important.
I got your point.
Well,
Okay.
Just 1 year before in Novosibirsk, I just performed some work on the same topic, and it's funny that my result was qualitatively look like for yours and those guys you previously mentioned, who also investigated toughness. So thank you for
questions.
Okay, so unfortunately we have no more time for questions. So thank you, Igor, once again. Very interesting talk.